Complex zeros and the fundamental theorem of algebra. The fundamental theorem of algebra says every polynomial p of x with a degree greater than or equal to 1 with complex coefficients has at least one complex zero. So now we are allowing for the coefficients to be complex numbers, not simply real numbers. And we are also allowing for our zeros to be complex. Now keep in mind that when we say complex, that includes real numbers, but it also includes non-real numbers. The complete factorization theorem says that if p of x is a polynomial of degree n, where n is greater than or equal to 1, then there exists complex numbers a, c1, c2, all the way up to cn, with a not equal to 0, such that p of x can be factored into a times x minus c1 times x minus c2, multiplied all the way up to x minus cn. And this basically just says that every polynomial can be factored into n linear factors if we allow for the zeros to be complex. So we'll use our first example here just to show how the factorization theorem works. So first we are going to factor p of x and or find the zeros of p of x. Now to do this, you could use synthetic division, but in this case, I'm just going to choose to use grouping because I can see that this particular polynomial is going to be easily factorable by grouping. So we can take out an x squared out of the first two terms, and that is going to leave us with x minus 3 left over. And out of the second two terms, there's really nothing in common here, but we can factor out a positive 1, which will leave us with, of course, just x minus 3. Now you can see we can take out the x minus 3, and what we have left over is x squared plus 1. Now this is not the complete factorization of p. What I'm going to do next is just go ahead and find the zeros. So to get the zeros here, we're just going to set each of these factors equal to 0. And of course, when we solve here, we get x equals 3. Now over here, when we solve, we're going to subtract 1 from both sides. And then we're going to take the square root of both sides. And that's going to give us x is equal to plus or minus I. So the zeros are 3, positive I, and negative I. So you'll notice that we have 3 total zeros. And now the complete factorization using these complex numbers, I and negative I, we can factor this into x minus 3, x minus I, and x plus I. And this is the complete factorization of p of x. Now in our next example, we'll go ahead and do the same thing. So find all the zeros and the complete factorization. Now this time, it's not as simple to factor this, right? Because it does not lend itself to grouping. So I'm going to go back to synthetic division. We have 1x cubed, 0x squared, negative 2x, and positive 4. And I know that I'm only going to be considering factors of 4. Now, I can kind of see that if I plug negative 2 in here, I'm going to get negative 8 plus 4, which is 0. So let me go ahead and use negative 2 in synthetic division here. Negative 2 times 1 is negative 2, and then we add negative 2 times negative 2 is positive 4, and then we add, and negative 2 times 2 is negative 4, and this gives us 0. All right, so we now know that p of x can be factored as x plus 2 times x squared minus 2x plus 2. Now that's not all the zeros, and that's not the complete factorization. So if I set x plus 2 equal to 0 and x squared minus 2x plus 2 equal to 0, here we get x equals negative 2, and here we're going to use the quadratic formula. And by the way, the reason I'm doing this is because this does not readily factor. So we have x equals 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 2, all divided by 2 times 1. And this is 2 plus or minus the square root of 4 minus 8 over 2. And that simplifies to 2 plus or minus the square root of negative 4 divided by 2. And we'll keep going here. This is 2 plus or minus 2i divided by 2. And this is 1 plus or minus I. So for zeros, we have x equals negative 2, 1 plus I, and 1 minus I. Now for the complete factorization, this is where it gets a little bit tricky. But if we continue up here, we have x plus 2, and then x squared minus 2x plus 2 can be factored into x minus the quantity 1 plus I and x minus the quantity 1 minus I. Now, if you simplify this just a little bit by removing some parentheses, you're going to get x minus 1 minus I and x minus 1 plus I. And this is the complete factorization of p of x. Next, we will briefly discuss the zeros theorem. Every polynomial of degree n, which is greater than or equal to 1, has exactly n zeros, provided that a zero of multiplicity k is counted k times. So for example, here we have a polynomial p of x. If I were to ask you for the zeros of this polynomial, you would probably tell me 1, negative 2, and negative 3. And this looks like 3 zeros. But we have to remember that because the factor x minus 1 is raised to the third power, the multiplicity of the 0, 1 is 3. And x plus 2 is raised to the second power, so the multiplicity of this 0 is 2. And the last 0 here is, or the last factor there is raised to the fifth power, so the multiplicity of that 0 is 5. So if you count up all those zeros, you have 10 zeros. So it's kind of like 1 is a 0 3 times, negative 2 is a 0 twice, and negative 3 is a 0 5 times. And so if you count all those up, you get the degree of the polynomial, which in this case is 10, right? If we just add up these powers. Oops. So yeah, n equals 10 down here. There we go. So if repeated zeros are counted independently, we get the same number of zeros as the power of the polynomial. In the next example, we want to find the complete factorization and all 5 zeros of the polynomial. And we know this polynomial has 5 zeros because it is a 5th degree polynomial. So first we can start by simply factoring out the greatest common factor, in this case, which is 3x. If we factor out 3x, we have x to the 4th power plus 8x squared plus 16. Now we can factor this by using basic factoring techniques. And so this becomes 3x times x to the 4th power will factor as x squared times x squared. 16 will factor as 4 times 4. And you can see that if we put plus signs in both spots, we will get the polynomial we had up there. So now this is equal to 3x times x squared plus 4 quantity squared. Now that is the complete factorization if you only want to factor over the real numbers. But if we take the factor x squared plus 4 and set it equal to 0, we can quickly discover that the solutions here are going to be positive and negative 2i. So that means that x squared plus 4 will factor into x minus 2i and x plus 2i. So if we want to factor our polynomial over the complex numbers, this would become 3x times x minus 2i times x plus 2i, right? So that's for the first factor of x squared plus 4. But then we can multiply by x minus 2i and x plus 2i again. And finally, we can write this as x minus 2i quantity squared and x plus 2i quantity squared. And this would be the complete factorization of p of x. Now, what are the zeros? Well, one of the zeros, of course, is 0 itself, because if we set 3x equal to 0, we get 0. And then we have the 0 2i twice and negative 2i twice. So those are the 5 zeros. Now, realistically, we only have 3 different zeros, but according to multiplicity, we do have 5 zeros. In the next example, we're going to work backwards. Here we want to find the polynomial when given specific zeros. So in part A, find a polynomial p of x of degree 4 with zeros I, 2, and negative 2, and p of 3 must be 25. So we'll worry about this part last, but what we do know is that p of x must be equal to a times x minus I, x plus I, x minus 2, and x plus 2. And this is just based on the zeros. So now we're going to multiply this out. And so first of all, we have a x minus I times x plus I is going to be x squared plus ix minus ix minus I squared. And x minus 2 times x plus 2 is x squared minus 4. Simplifying, we can see that ix and negative ix cancel. And also, negative I squared is negative 1, which is positive 1. So this becomes a times x squared plus 1 times x squared minus 4. Now we can continue to multiply this out. X squared times x squared is x to the 4th power. Then we have negative 4 times x squared and positive 1 times x squared, which is negative 3x squared. And then 1 times negative 4 is negative 4. And this is p of x. Now please understand that a can actually be any number except 0, and that will not affect the zeros of the polynomial. However, we have additional information that p of 3 must be 25. So this means when we plug in x equals 3, p of x must be 25. So 25 must be equal to a times 3 to the 4th minus 3 times 3 squared minus 4. And this is a times 81 minus 27 minus 4. And so 25 is equal to a times 50. And so a must be equal to 1/2. Now if we plug 1/2 back into here, we know that p of x is 1/2 times x to the 4th minus 3x squared minus 4. And if we distribute the 1/2, we end up with 1/2 x to the 4th minus 3/2 x squared minus 2. And so this is the answer to part A. Now for part B, it is very similar, except that now we want the zeros to be negative 2 and 0, and negative 2 is a 0 of multiplicity 3. And they also do not tell us any additional information like they did in part A. So for part B, we know that q of x must be equal to a times negative 2 is a 0 of multiplicity 3, so x plus 2 to the 3rd power. And 0 is also a 0, and so that's just going to be times x. So now we need to multiply this out. We have ax, and then x plus 2 times x plus 2 times x plus 2. And I'll spare you the details here, but when you multiply x plus 2 times x plus 2 times x plus 2, you're going to get the following. And when we distribute ax to this, actually we'll just distribute the x. So we'll get ax to the 4th plus 6x cubed plus 12x squared plus 8x. And this is what q of x is. Now a, in this case, can actually be any number. So I'm just going to choose a to be equal to 1. So then q of x would be the polynomial x to the 4th plus 6x cubed plus 12x squared plus 8x. In the next problem, we want to find all 4 zeros of the following polynomial. So when you first get a problem like this, it's natural just to start trying some synthetic division to see if we can discover one of the zeros, because once we know one of the zeros, that will help us find other zeros. So I'm only going to be considering factors of 4. So I could try 1, for example, and let's see what we get for that. And so we can see that 1 is not a 0. Let's try -1. Okay, we can see that -1 is also not a 0. So what are our other choices here? Well, another factor of 4, of course, is 2 and also -2. So let's try 2. And 2 works. So we now know one of the zeros. Let's see if we can find another 0. So we could try 2 again. But actually, I don't think 2 is going to work here. So let's try -2. Let's see what happens here. And we can see that -2 does not work. So this means we now have to consider the factors in front here. So we have the factors of 2, right, divided by the factors of 3. So that would be the numbers 1 and 2 divided by the numbers 1 and 3. So we need to consider things like 1/3 or 2/3. So let's go ahead and try 1/3. So 1/3 times 3 is 1. 4 plus 1 is 5. 1/3 times 5 is 5/3. And 7 plus 5/3 is 26/3. 1/3 times 26/3 is 26/9. And clearly we can see we're not going to get 0. So let's try -1/3. -1/3 times 3 is -1. 4 plus -1 is 3. -1/3 times 3 is -1 again. 7 plus -1 is 6. And -1/3 times 6 is -2. And there it is. We have another 0. Now, as soon as we get to 3 numbers left, we know that this is a quadratic. So that means that we can now factor p of x into x minus 2 times x plus 1/3 times 3x squared plus 3x plus 6. All right, so now we're going to find the zeros for the last part here. Notice that there's a 3 that we can factor out. So if I pull that 3 all the way out to the front of this polynomial, this will become x squared plus x plus 2. So now let's find these zeros. So for that, we're just basically setting this quadratic equal to 0. And we're going to have x equals -1 plus or minus the square root of 1 squared minus 4 times 1 times 2, all divided by 2 times 1. This is -1 plus or minus the square root of -7 divided by 2, which is -1 plus or minus I radical 7 over 2. So these are the other zeros. So the zeros of this polynomial are 2, -1/3, and then here we have 2 zeros. One of them is -1/2 plus radical 7 over 2 times I, and the other one is -1/2 minus radical 7 over 2 times I. So what you might have noticed in the previous problems where we had complex roots is the following theorem, the conjugate zeros theorem, which states that if the polynomial p has real coefficients, and if the complex number z is a 0 of the polynomial, then the complex conjugate of z, which they call z bar, is also a 0 of the polynomial. So what that means is that if a plus bi is a 0, then a minus bi is also going to be a 0. So let's use this to do the following problem. So it says to find a polynomial p of x of degree 3 that has integer coefficients and zeros 1/2 and 3 minus I. So the zeros are 1/2 and 3 minus I. However, since the polynomial has integer coefficients, and integers are also real numbers, this means that the other 0 must be the conjugate of 3 minus I, which is 3 plus I. So these are the three zeros of the polynomial. So p of x, the polynomial, will be x minus 1/2 multiplied by x minus the quantity 3 minus I multiplied by x minus the quantity 3 plus I. And now we just need to multiply this out. So this is a little bit tedious, and there are different ways to do this, but you could just distribute the negative on the inside of the parentheses here, and then just make sure you multiply everything in the first set of parentheses to everything in the second set of parentheses. So we're going to do all of these 9 multiplications here. And so this gives us x minus 1/2 times, so we're going to go through these now. X times x is x squared. X times negative 3 is negative 3x. X times negative I is negative ix. Now we'll move to negative 3 times x, which is negative 3x. Negative 3 times negative 3, which is positive 9. Negative 3 times negative I, which is positive 3i. And finally, I times x is positive ix. I times negative 3 is negative 3i. And I times negative I is negative I squared. Now this looks terrible, right? But a lot of stuff is going to cancel out. So let's see what we have here. We have a negative ix and a positive ix, a positive 3i and a negative 3i. And then we have some like terms. So we've got negative 3x and negative 3x combines together. Positive 9, and then let's remember that negative I squared is negative 1, which is positive 1. So here we have positive 9 and positive 1, which is going to be 10. So this becomes x minus 1/2 times x squared minus 6x plus 10. Now we're going to multiply this out. Oh, and also I forgot to mention that, there is an arbitrary value a in front of this. Let's go ahead and put that in. Now I'm just going to go ahead and multiply this out. Now, one thing I could do, see, I kind of noticed that if I multiply these, I'm going to have some fraction values being multiplied here. Now that's perfectly fine, but what you could do is you could just let a equal 2, for example, and then distribute that 2, and that'll get rid of that fraction. So I'm actually going to do that. I think it's worthwhile to do that here. So if I just let a equal 2, this is going to be 2 times x minus 1/2 multiplied by the rest. And that is 2x minus 1 when you multiply that part out. And now I can comfortably multiply out the rest here. So 2x times x squared is 2x cubed. 2x times negative 6x is negative 12x squared. 2x times 10 is positive 20x. Negative 1 times x squared is negative x squared. Negative 1 times negative 6x is positive 6x. And negative 1 times 10 is negative 10. And then combining like terms here, we have the following. And so this is my p of x. Now keep in mind that you could have a different answer. I chose a to equal 2, right? And that's why we have a 2 here. If you would have chosen a to equal 1, for example, then your polynomial would have been a little bit different, right? It would have basically divided all of these numbers by 2. And so that would have been x cubed minus 13 halves x squared plus 13x minus 5. But the reason I chose a to equal 2 is because I didn't want to have a coefficient like this. Okay, but this is correct, technically. Oh, wait a second here. I beg my own pardon here. They do say integer coefficients, don't they? So the fact that they say it has to have integer coefficients means that we actually cannot have this in the end. So I'm going to leave this in the video because, this is okay in terms of the polynomial having the zeros that they prescribed. However, since they said it has to have integer coefficients, this is not a possibility. Okay, so our answer is the one that we got originally. And finally, we have the linear and quadratic factors theorem. Every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors, all of them also with real coefficients. So for example, let p of x equal x to the fourth power plus 2x squared minus 8. We want to factor this polynomial into linear and irreducible quadratic factors with real coefficients, and then we will completely factor it into linear factors, which would be allowed to have complex coefficients. So first, let's just recognize that the original polynomial can be factored fairly simply by using x squared and x squared, and then we'll use minus 2 and plus 4. And you can pause this to double check to make sure that this is equal to the original polynomial, and I assure you that it is. Now, x squared minus 2, if you set that equal to 0 and solve for x, you will get irrational numbers, radical 2 and negative radical 2. So we can still factor x squared minus 2 using real numbers, radical 2 and negative radical 2, right? However, x squared plus 4, if you set that equal to 0, you're going to find out that x is equal to plus or minus the square root of negative 4, which is plus or minus 2i, and those are complex numbers. So if we want to factor this into linear and irreducible quadratic factors, this is where we would stop. And so this is the answer to part A. For part B, they say go ahead and factor it completely into linear factors, and now we are allowing to have complex coefficients. So for part B here, you would just complete the factorization by simply using 2i and negative 2i as zeros. And so if you do that, this would be the answer. So please understand that both of these are the same. It's just that one is factoring without using complex coefficients, and the other one is factoring with using complex coefficients. And that concludes this video lesson.